Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Max Planck's articulation of quantum theory in 1900 represents a watershed moment in the annals of physics, irrevocably altering our comprehension of energy, matter, and the fundamental nature of the universe. This essay delves into the genesis, substance, impact, and legacy of his groundbreaking work, examining its historical context, intellectual precursors, subsequent reverberations across the scientific lands. The closing years of the 19th century witnessed an interesting scenario. Classical physics, built largely upon the edifice erected by Isaac Newton and refined by luminaries such as James Clerk Maxwell, held sway. This framework achieved remarkable success in explaining a vast array of phenomena, from the celestial dance of planets to the behavior of gases. However, certain perplexing observations stubbornly resisted assimilation into the seemingly comprehensive worldview. One such enigma was the problem of black body radiation. A black body, an idealized object that absorbs all incident electromagnetic radiation, presented a theoretical challenge. Classical physics predicted that the energy radiated by a black body at shorter wavelengths should increase without limit, leading to what was termed the ultraviolet catastrophe. Experiments, however, revealed a very different picture. The observed spectrum exhibited a peak at a specific wavelength, decreasing at both longer and shorter wavelengths, a profile that classical theory singularly failed to reproduce. Several physicists grappled with this conundrum. Wilhelm Wien proposed a distribution law that accurately described the short wavelength behavior of black body radiation, yet it failed to align with experimental data at longer wavelengths. Similarly, the Rayleigh-Jeans law, derived from classical equipartition theorem, accurately predicted the long wavelength behavior, yet collapsed disastrously at shorter wavelengths, amplifying the ultraviolet catastrophe. These failed attempts highlighted a deep-seated crisis within classical physics, pointing towards the inadequacy of its fundamental assumptions when applied to the realm of microscopic phenomena. Enter Max Planck, professor of theoretical physics at the University of Berlin. Planck was deeply invested in the problem of black body radiation. He approached the problem with a meticulous rigor, meticulously studying existing experimental data and theoretical models. Planck, initially a staunch believer in classical physics, progressively explored radical departures from established principles to reconcile theory and experiment. In a stroke of intellectual boldness, Planck made an assumption that foo in the face of classical dogma. He posited that energy, contrary to classical expectations, was not emitted or absorbed continuously, but rather in discrete packets or quanta. The energy of each quantum was proportional to the frequency of the radiation, defined by the equation E equals h nu, where E represents energy, h represents Planck's constant, and nu represents frequency. This constant, h, now known as Planck's constant, has a value of approximately 6.626 times 10 to the minus 34 joule-seconds. Planck presented his revolutionary hypothesis, his quantum hypothesis, on December 14, 1900, at a meeting of the German Physical Society. This date marks the birth of quantum theory. His proposed formula, based on the quantization of energy, perfectly matched the observed black body spectrum across all wavelengths, resolving the ultraviolet catastrophe and ushering in a new era in physics. It is worth noting that Planck himself initially viewed his quantum hypothesis as a mathematical contrivance, a convenient trick to obtain the correct result, rather than a fundamental property of nature. He spent several years attempting to reconcile his quantum theory with classical physics, hoping to eventually eliminate the need for energy quantization. The immediate impact of Planck's work was substantial, albeit initially met with skepticism from some quarters. His formula garnered widespread acclaim for its remarkable accuracy in describing black body radiation. However, the radical nature of his quantum hypothesis, the idea that energy existed in discrete packets, was difficult for many physicists to accept. It challenged the deeply ingrained classical worldview that had dominated scientific thought for centuries. He derived his radiation law by introducing the concept that energy is quantized, a notion deeply unsettling to his contemporaries. One of the earliest and most significant validations of Planck's quantum hypothesis came from Albert Einstein. In his 1905 paper on the photoelectric effect, Einstein extended Planck's concept of energy quantization to explain the emission of electrons from a metal surface when illuminated by light. Einstein proposed that light itself consisted of discrete packets of energy, later termed photons, with energy proportional to their frequency, E equals h nu. Einstein's explanation of the photoelectric effect, which earned him the Nobel Prize in Physics in 1901, provided compelling evidence for the reality of energy quantization and solidified the foundation of quantum theory. Niels Bohr further advanced quantum theory in 1913 with his model of the hydrogen atom. Bohr proposed that electrons could only occupy specific orbits around the nucleus, each with a discrete energy level. Electrons could jump between these energy levels by absorbing or emitting photons with energy equal to the energy difference between the orbits. Bohr's model successfully explained the discrete spectral lines observed in hydrogen, providing further support for the quantum nature of matter and energy. These early successes of quantum theory in explaining black body radiation, the photoelectric effect, and atomic spectra established its power and potential, leading to its rapid development and application across diverse areas of physics and chemistry. The subsequent decades witnessed an explosive growth of quantum mechanics, leading to the development of entirely new formalisms and interpretations. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and many others made pivotal contributions, establishing the mathematical framework of quantum mechanics and extending its reach to encompass a wide range of phenomena. Heisenberg's uncertainty principle, formulated in 1907, introduced a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, could be known simultaneously. Schrödinger's equation, published in 1906, provided a mathematical description of the time evolution of quantum systems, analogous to Newton's laws of motion in classical mechanics. Dirac's relativistic quantum mechanics, developed in the late 1920s, unified quantum mechanics with special relativity, predicting the existence of antimatter and laying the foundation for quantum field theory. Quantum mechanics has had a transformative impact on our understanding of the physical world, revolutionizing numerous fields and enabling technological advancements that were once considered science fiction. Its applications extend far beyond the realm of fundamental physics, permeating chemistry, materials science, electronics, and many other disciplines. Transistors, the building blocks of modern computers, rely on the quantum mechanical properties of semiconductors. Lasers, used in a wide variety of applications from medical surgery to barcode scanners, are based on the principle of stimulated emission, a quantum mechanical phenomenon. Magnetic resonance imaging, MRI, a powerful diagnostic tool used in medicine, exploits the quantum mechanical properties of atomic nuclei in magnetic fields. Nuclear energy, both for peaceful and military purposes, is governed by quantum mechanical principles. Despite its undeniable success, quantum mechanics continues to pose profound conceptual challenges. The interpretation of quantum mechanics, the attempt to understand the meaning of its mathematical formalism and its implications for the nature of reality, remains a subject of intense debate and investigation. The Copenhagen interpretation, the dominant interpretation, favoured by Bohr and Heisenberg, asserts that quantum mechanics describes probabilities rather than definite properties and that the act of measurement fundamentally alters the state of a quantum system. Other interpretations, such as the many worlds interpretation and Piot wave theory, offer alternative perspectives on the nature of quantum reality, each with its own strengths and weak. Furthermore, the unification of quantum mechanics with gravity remains one of the greatest unsolved problems in physics. Einstein's theory of general relativity, which describes gravity as a curvature of spacetime, is incompatible with quantum mechanics, which treats gravity as a force mediated by hypothetical particles called gravitons. String theory and loop quantum gravity are two leading approaches attempting to reconcile these two fundamental theories. A complete and consistent theory of quantum gravity remains so. Max Planck's 19th articulation of quantum theory stands as a towering achievement in the history of science, forever altering our understanding of the universe. His daring hypothesis of energy quantization, initially met with skepticism, ultimately revolutionized physics, paving the way for advancements in quantum mechanics and enabling technological innovations that have transformed society. While conceptual challenges and open questions remain, the enduring legacy of Planck's work is undeniable. It serves as a profound reminder of the power of human ingenuity to challenge established paradigms and to unlock the deepest secrets of nature. The intellectual journey that began with Planck's resolution of the black body radiation problem continues to this day, inspiring scientists to push the boundaries of knowledge and to explore the mysteries of the quantum realm. His accidental stumble upon quantization, initially viewed as a mere mathematical trick, has evolved into a cornerstone of modern physics, a testament to the unexpected and transformative power of scientific inquiry. The implications of Planck's discovery will continue to resonate throughout the scientific world for generations to come.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.